Hello everyone, welcome back to Structure Expert. Now we have to compare about taper section, okay, taper frame with whole frame hollow section, and also compare with the truss frame. We will talk about analysis, design, and the total weight of the frame, okay, and what is different between those three frames. Now let's start from the beginning. We have to compare taper section with you hollow section and with you truss, and we'll go in deep in the next part. Now we scroll down to the part. Okay, this one we talk about the geometry. You see here we have a tutorial about how to design photo frame, how to design truss. You can check in my YouTube channel about the tutorial, and we compare with the same geometry. Okay, the width length is 34 meter length, and the column height is 6 meter length, and overall height is 8.2 meter. And it is the same with the taper section. This one is taper section. It's most popular in American standard. Okay, use this section for the economic, for the seal vest, and for the easy installation to save time in construction. And now we have to talk in depth about this to compare with the other frame, other system. And this one we use the taper column and taper beam or taper raster in this segment, and lower and small segment at the end. Okay, and we will check the real section in the middle, but in this slide we have just introduced you about the system and compare you quickly, and then we will check each section and the thickness of the section, and the strength of the section in actual model. Okay, and this one also the same geometry. Okay, we use the 34 meter, and the column height is 6 meter, and it's different between the overall height for the truss. Okay, we has a slope is the same, but the truss you have the geometry is not the same with the raster. Okay, but the overall section, the overall system is the same. Okay, now we have to check about the load. In this one we use the same load. For the apply load we use the same. In this one is for the deload. Okay, 1.8 kilonewton per meter. And also for the light load we use, for the light load on rods is 2.4 kilonewton per meter. We use 0.4 kilonewton per square meter for the shoe light load on rods for the zero coat, and the bay width is 6 meter, so you multiply 0.4 with 6 meter is equal this value. And this one for the wind load we apply for the internal pressure only, not include the CPI. Okay, we use the maximum load care to discuss in this one, the maximum at the column, and for the rods. Okay, for the wall and for the rods. Okay, for the wind load we use the one load combination, one load cast, maximum load cast to compare. And you can use for internal pressure include in your analysis, but in the case I use for the internal pressure only, not include internal pressure. Okay, now we just summarize about the apply load. We apply for the load, light load, okay, row load, and apply the light load, but light load on rods. The load we apply is 0.3 kilonewton. Okay, the load we apply it for the 0.3 kilonewton per square meter and for light load we use 0.4 per square meter. Each issue light load, okay, 0.4. Reduce light load on rows, okay, category H, okay, and wind load we apply for the internal pressure only, not include internal pressure, okay, and our wire width is 4 meter. So you can multiply with the way you can got the value. I show you a previous slide, and we apply wind load for the internal pressure only, and we include notional load. We use the maximum one is 0.3%, both initial plus initial sway, okay, for global imperfection, okay. Now you know about the condition of load applied on our structure. It's the same. We apply it for the 3 systems, for the taper section, for the hot roof section, and for the truss frame. And the analysis type, we use the first order analysis, second order analysis, and include backlink. And the analysis we include the global imperfection, okay, that I showed you in previous slide about the notional load. We apply notional load with the initial sway. Now I just display you about some right design or deflection. The case you see here is the taper frame. Deflection for the taper frame we talk only in the Z direction. Actually we have deflection in both direction, in Z, okay, in Z down, go down, and in H can go in sideway, okay. So we discuss about maximum deflection in Z direction, and at the end slide we will discuss about both directions. You see here indicate the maximum deflection is minus 163 millimeter for taper section. We use this system, okay, at the the joint. We use the larger section and distribute to the smaller section, okay. At the pitch, use the smaller section. This one is the same. We use the taper column and taper raster, and you see here about the maximum deflection in the direction. Here for the serviceability limit state, we talk about deflection. We talk in the serviceability limit state, okay. Now let's start to the taper section. You see here the taper section, deflection is around 117.7. We use the hot roof section, okay. We use the hot roof column, we use the hot roof raster, and use hole connection. You see here the deflection is smaller than the taper frame, because the taper frame use the smaller section, smaller thickness than the hot roof. So we have to compare with the deflection, and also compare with the strength. And to make sure to pass our requirement for design, we have to pass both in strength design and deflection design, or serviceability design, okay. Here for the hot roof section. And the last one is for the truss frame. We use the the whole through section. We use the standard section to design this frame. Okay, you see here the maximum deflection is only 75.1. It's very good in deflection. If you consider in the deflection, you can choose the truss frame system. It's very good to control in both deflection in Z direction and X direction, and also good stability for truss. Okay, you can check which one is most better and relevant with your requirement, and you also compare with the total weight or the structure, and compare with the fabrication time and how long you can complete your project if you choose your truss or you choose your taper or you choose your hot section, and compare with the cost. It is very important in your construction. So now we focus about the design, total weight, and we not talk about the fabrication, installation inside about the labor, but you can compare all, and you can include about how which you can include about which system issue your cost, either construction time and the money or the budget. Okay, now we have to summarize about our system. We use the taper and hot rule and truss, and for the material we design taper in class because steel strength is 355. If you use the same with the hot rule strength, it's not pass. And the design for taper is designed as the wear. Okay, where section we not design as the standard section, but hot rule you can design as the standard section because it's come from the factory. Okay, we use the standard section, and truss also use the standard section. Okay, for the truss. And the geometry we can use it the same as I showed you in the previous slide. You can check it's very similar. It's different in truss, is different height, but we can take it as different geometry and section. We will check it more in model. After complete this slide, we will go forward to the model and check it. And the loading we apply the same for the load line load, and we apply the same on each frames. And the analysis we apply the same, apply the first order analysis, second order analysis, buckling. We apply notional load, we apply the initial inflection, we apply the same. And now we talk about the deflection in the Z direction. I just showed you in the previous slide. You can check, you can come back and check again, and you see here this one also include the X direction. You see here in taper frame we can consider in minus, okay, minus and plus direction. In this one you can check is the 21.1. in the combination include the load and line load, and 19.1 is combination for the load and with load. Okay, you can check about the horizontal deflection, and for the hot rule the horizontal deflection. So this system for the horizontal deflection is almost the same, but it's too much different in vertical deflection for hot rule and taper section. And for the truss you can see here the deflection in each direction is similar with hot rule, and for the vertical deflection is very good if you compare with the two frame system, taper frame system and hot rule frame system. You can check here it is very good. In Z direction is only 35.1 millimeter, and the maximum ratio in this one we can check about section design in elastic or in plastic or in interaction, but almost different controlled by global stability resistant. Global stability resistant. Global stability resistant is control the design or those three frame. Okay, taper, hot glue, and truss. And these two type of frame, hot glue and truss, the maximum design ratio is 85.3%. It's the same 85.3%, but higher for the taper section is 91.7%. We talk about 2D frame, but we also design in 3D frame. We compare in 3D frame, we can get the more accurate. Now we talk about 2D frame. Okay, in the case, and you see here it is the total weight of frame. For the taper, the total weight is 3.2 tons, and for the hot glue is 4.69 tons, and for the truss is 2.74 tons. You see here in the comparison, the unit weight of truss is smaller than other two types, and the design control is deflection is very good. But for the taper, you see here the total weight is only 3.2, but it fell in the deflection. You see here the deflection is 163.0. It's over the permissible deflection. So in the case you have to increase more section to have another thickness to reduce deflection. Okay. So in the hot glue, the 4.69 tons, because you hot glue section to pass the deflection. Okay, so if you reduce then lower than that section, the total weight will be reduced, but you cannot pass the design deflection. So we keep the hot glue section. The unit weight is 4.69 tons. So you can check about the section of each model later. We will show you detail about the section of each model. Okay, so should remember about the fail in design is not only for the strength. For the strength it pass, but for the deflection is not pass. It is very common mistake that when you design you have to check both for strength and for the serviceability to make sure your structure is safe again about the strength and about the deflection. If you don't care about deflection, okay, you can use taper and got the lowest unit weight. Okay, is around 4.2 if compared with hot glue section. Okay, thank you. Now we have to check in the model. Okay, in the model is the hot glue. The hot glue we use the column. I show you about the column. Okay, this one we use at the bottom is 350 and at the end is 700. And for the raster we use the section 750. Okay, 750, and at the end is 300. You can check about the parameter of the section. Okay, this one is the initial section. Okay, it is the width u 200 and the edge. Okay, edge overall height of the section is 350 and the thickness of plank is 12 mm and the thickness of web is 8 millimeter here, and this section is 200 multiplied with 350. Okay, and you can increase it to this section at the end is 700. Okay, 700 is not here, is at this location. When you include joint, you remain in this location. Is the connection between the raster and the column at this location. Okay, but actually 700 is in here. You see here, you can check at here is 700, but actually your section is designed only in the connection between the raster and the column in the location, is not the location. Okay, you can check. And now we have to check about you can check, sorry, now we have continue to truss. Okay, you see here the geometry is the same, we use the same geometry, and for the column is IPE 250, and for the bottom and top chord is 200 multiplied 80 multiplied 60 is standard section, and for the diagonal we use 60 multiplied 40 multiplied 3 millimeter. Okay, we use it the same. It is for the steel truss. And you can check about the load. Okay, this one we apply okay, the load 1.8, we apply like load 2.4, and below is 3.37, 2.54 and 2.66. Okay, and we will check compare each other about the load to make sure it's the same for the load, for the light load, and for the wind load. Okay, it's the same. And this one for the taper for the whole section. Okay, whole connection. We can compare each other. And for the geometry, okay, and for the load we apply the same, and another load is global. Okay, global inflection. You can see here it is for the national load, we apply for the national load, and we include it in the load combination. And initial phase, okay, you can check here about initial phase, and after that you can run analysis. In analysis we include the initial phase, okay, we include the second order analysis, and after that you can run analysis. You can check about the deflection. You can see here the deflection insufficiency. You can check it is for global check. For design, we include the second order analysis and check for the buckling. Okay, you can see here the maximum ratio is 91.7. okay, and the location 91.7, and the control design is global stability resistant for the taper section, and for the whole section, okay, we use the IPE 550 for column and IPE 500 for the raster, and we use the whole connection. The whole connection is the section cut from the IPE 500, and for the load we use the same, the load, line load, and wind load, and we also include for the apply notional load and apply with the condition, and initial sway we apply it the same. And for the analysis, you can check, we include the initial sway and we include the second order analysis and design. Now you can check, we have to continue about the global. The design, we perform the second order analysis, and you can check here, and you can apply the calculation. Okay, now I can start and apply it from the analysis. You can rerun again to make sure. Okay, this is the view I show you. You can see here no readable buckling, and now we have to go over to design. Okay, you can check it. Okay, this is the utilization of the maximum view in the location. And now this is for the overall dimension, and for the section. Okay, you can check about each section, and we also apply the load. We use the same load, the load, line load, and wind load. Okay, we use the same. In this one you can apply the national load, and you can also apply the initial sway. And we include the initial sway, and you can perform either second order and further analysis, and you can check here about the deflection. Okay, about the deflection and global check. Okay, you can check about the global check and calculate its again. you see here the maximum value is around 85%. Okay, and the maximum deflection is around 75.2. Okay, 75.2. okay, it's around here. It's 75 millimeter. This for the global. Okay, global check. The design control is the global resistance, you can check here, and it is the total weight for the steel truss. Okay, the total weight for the steel truss. And okay, now you can compare the total weight of each structure. Okay, by clicking here, it is for the truss is 2.74 tons. Okay, I show you in the summary here is 2.74 tons for the truss. And now let's continue to the taper frame. Okay, is 3.2. okay, is 3.2. you can check here, 3.2. okay, 3.2 tons. In for the last one is the hot roll section, is the whole connection. Hot roll section is 4.7 tons. okay, 4.69 tons. okay, in the US we just compare the frame, we not include for the purlin and for the other section. We compare the frame, okay, the column, the raster, and we compare the truss is the same for the column and the diagonal and the upper and lower chord. okay, we not include the restraint and not include the purlin. okay, we include only for the net frame as in this model. okay, you can see here